We are back here at the Cardiovascular Lab here at the Johnson Space Center. I'm joined by Steve Platts, who is one of the laboratory managers here at this laboratory. You know, before we were talking about these ultrasounds that they have here on the ground that is very similar to what the crew up on board the station has. Steve, talk a little bit about the upcoming experiment called, what is it, Cardiooxy?
Yeah, Cardiooxy. You talked a little bit about ICV earlier, and that one is focused on the heart. Cardiooxy is focused on the blood vessels.
Okay.
And so we would get images like this. This is an image of a carotid artery, and you see these colors streaking by. That's Doppler. So if you think about the radars you've seen when we're looking at weather and they're showing how the winds and the rains are moving, and it's Doppler color, this is that same concept. It shows the colors moving, so this represents blood flow. So we'd measure that, and we'd measure the diameter of the vessel, and we can actually measure the thickness of the blood vessel. And on the ground, that thickness has been shown to relate to risk of atherosclerosis. So that's really what we're trying to get at. Is spaceflight at all changing the risk of getting atherosclerosis down the road for our astronauts?
Okay, so you take, is this, where do they take this? Is this an artery in the neck?
Yeah, right here in the neck. And
Okay.
so you take a probe like this, and you
just stick it up there and take a look at it. Now, do they do it to themselves, or do they have a fellow expedition member help them out?
We've done it both ways.
Okay.
And for this one, I believe we're going to have them do themselves, and we're going to have someone on the ground do the remote guidance like we talked about for the previous study.
So you're talking about the different colors and the Doppler effect. I mean, that's just like what you see on the weather, you know, every night, taking a look at it. So the blue means that's...
So the blood flow is moving that way, in that direction.
Do you take a look at how fast it's going? I mean, does that tell you something?
We do. We can look at velocity, and then if you multiply velocity by the cross-sectional area, you can actually get the blood flow. And blood flow tends to be what we use more, how much blood is going through that vessel in a minute or whatever time period you choose to use.
So you can actually see the walls here, right? I mean, you can see them expanding and contracting.
Yep, so that's the pulsatility you'll see in an artery.
Yeah. So let's talk about how small, you know, we were talking about this earlier before we came on the air, talking about portability. I mean, this is no bigger than a laptop, right?
Right.
Now, let's take a look over here to the right. This is what they used to have on board the International Space Station, something this size. It was about the size of an entire rack,
It was a full rack, yes.
So what?
It took up a lot of space, and it's locked in place. So you have to do everything within a cable length. You can't move around the station. With the new unit here, it's portable. You can see how small it is. You can move it around station. You can have a lot more flexibility with the experiments you want to do with it.
I mean, it's fascinating to see something this large can now be done with something that's just, you know, weighs almost nothing and takes up just the same size as a laptop computer.
And this has much more computing power than the ultrasound that was up there previously. There's a lot more we can do now than we could do before, even though the unit's fraction of the size.
This is the same sort of thing that hospitals use, right?
Absolutely.
Okay. So are they seeing sort of the same thing, things going smaller and smaller and smaller
Yes.
as the years
In fact,
go by?
we leverage off of those technological breakthroughs. We are constantly watching the field to see what's coming up, what's new. Our long-range vision would be like a tricorder. Just like we'd want to be able to just scan like this with a tiny little handheld unit, and that's all we need, or iPod, iPad, something like that. But that's where we see it going in the next 10 years. Very small, handheld medical devices that we can do everything right then and there.
With a lot more power. So let's talk about Cardiooxy again. When the equipment's up there, this is up there.
Yes, this is up there now, and it's being used for ICV and some other experiments right now.
So how long will Cardiooxy last? Like what's the length?
Well, that's a really unique part of this study is Cardiooxy, the data acquisition in flight should take about 4 years, but we have a 5-year surveillance period after they land, so we can track any increased risk that the crew member acquired while they were in space. And so this is the first time we've been able to do a surveillance portion of a study. So the total study is 9 years, and that's very, very rare for an ISS study.
Whenever you take a look at, you know, we talked about before how the human body reacts to being up there in space, and is it one of these things where you guys study it and you sort of solve these mysteries, or is it one of these where the more you look into it, you sort of, you know, peeling back the onion, you just learn more and more about how the body, you know, are there more mysteries than you guys even anticipated?
Oh yeah, every time we do an experiment, we end up with more questions than we had when we started the experiment. And that's not to say we don't make breakthroughs, we do. We can come up with countermeasures. We've developed a few countermeasures. Some of the other laboratories have been working on countermeasures for various things. But every time you do a study and you see something like this, and you think you know what you know, you find out that you really don't know that much at all.
Now, last question real quick. You know, we talk about the benefits of here on Earth. What is this sort of experiment and the one we talked about before, ICV, what does that really, how does it impact people here on Earth? And talk about the differences between being in space and being here on the planet.
Well, we know on Earth, if you have thickening in this vessel, that it has a negative consequence later on for atherosclerosis. And we're doing other parts of this experiment where we look at how the vessels function, so how they get bigger and get smaller. And those are all things that are used in the clinic to diagnose cardiovascular health, to see how the endothelium's working, to see what precursors might be going on before you actually get atherosclerosis. So this is all subclinical. You would not have symptoms if we were to detect something. It's very, very, very early on. And the earlier you can detect things like this, the earlier you can treat them, and your chances of positive outcomes are even greater. So when we're doing these kind of experiments, they're all designed to relate back to the clinic. How can we bring it back to Earth and help the people down here?
So basically we can learn, the warning signs of a variety of different issues with the veins and the arteries and the heart way earlier on than we ever could by learning what happens up in space. It's fascinating. It's fascinating stuff to see this, to see how this actually operates here on Earth versus up there on board the station, to see what the crew is doing. I mean, they almost have to sort of become their own sort of, doctors without, all the technical expertise of it. But it's fascinating to see this kind of stuff happening. So if you want to learn more about this, you can always log on to the NASA website, nasa.gov/station. Take a look at all the different experiments that are taking place on board the space station right now, and read about Cardiooxy, or the ICV experiment that we talked about before, and take a look at what the crew is working on with these scientists here on the ground.